All right, so today's lesson is still Unit 1, Chapter 1, Kinematics, Lesson 8 on relative velocities. So what is a relative velocity? A relative velocity is simply a velocity measured from someone's point of view. So what do I mean by that? So we're going to do quite a few thought experiments today, and I'm going to try some demos, but I don't have as much space, and all I have is a tennis ball. But let's start with our first thought experiment. Let's say you're driving in a car, and you're on the highway, you're going 100 kilometers per hour. Okay, and there's a person at the side of the road, just standing there, and as that person looks at you, he sees your car zoom past him at 100 kilometers per hour. But now let's say you have another car driving next to you, also move at 100 kilometers per hour. If a passenger in that car were to look at you, would they see you zoom past them at 100 kilometers per hour? No, they wouldn't. They would just look at you and see you as if you're not moving relative to them. And to them, you aren't moving. Okay? To them, everything else, the trees and the observer sitting at the side of the road, is moving past them in the opposite direction at 100 kilometers per hour. So this is what relative velocity means. Okay, it's velocity measured from someone's point of view. And when we say someone's point of view, we use the term frame of reference. So frame of reference is a coordinate system relative to which motion is observed. Okay, so let's try another example. I'm just going to move this back. Let's say I have the tennis ball and I throw it straight up. That's the ceiling, so it can't go too high. But I throw it up and it comes straight back down. Exactly what you would predict. But what if I was moving at a constant velocity? This is important. We'll talk about frames of reference next chapter when we're accelerating. But today, just constant velocities. If I walk forward and I'm moving at a constant velocity and then I throw it straight up, will it come straight back down to my hand? Or will my hand have moved forward by the time it comes back down? What do you think? Make a prediction. We'll do it. Kind of down a bit. And as I move forward, down, straight back down. So it actually comes right back to your hand. And why is that? Well, think of it in terms of components. Components is a great way to think of things. As I'm moving this way, I'm moving this way, and the tennis ball is moving this way. I throw it up, so I do apply a force to change its motion in our y component, and so it goes straight up. But I have not applied any force to accelerate it in x. That means it's still moving horizontally with me. Now, from my point of view, as I'm moving, it just looks like it goes straight up and down. But from your point of view, a stationary observer next to me, it looks like it undergoes some sort of projectile motion. Now, the great thing about physics is all the laws of physics work in all frame of references. So if you were to analyze it as a projectile from your frame of reference, you would be able to predict its motion. If you were to analyze it as a projectile from my frame of reference, you would still correctly be able to predict its motion. So in a sense, when we talk about frames of reference, it's really hard to imagine what something at rest would be. And I can say something is at rest, but at rest relative to what? You can say the school is at rest, but I can come up to you and say, yeah, well, I can move the school. And I could do it quite easily without any machinery. It's actually quite simple. All I have to do is walk away from it, or towards it, or to the side of it. Doesn't matter. Once I start moving relative to the school, from my point of view, I'm at rest, but the school is moving. That's that simple. And there's nothing wrong with saying that. That is 100% correct according to the laws of physics. So let's think of another example. This is actually question 1 on the back, but let me draw this out. Tennis ball. let's say we're going to go canoeing. We have a river. Okay, so this river, the width is, let's say, identical all the way down the stream. And we also have a current. Okay, the current's moving this way. Now over here, we're going to have 3 canoeists. Now these canoeists are identical to each other in strength and everything else, meaning in still water, if they were to have a race, they would all tie each other. It'd be a perfect 3-way tie. But here's the goal of this race. The goal of this race is to reach the other side of the river first. Doesn't matter where, right? You can get to the other river here, 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 here. On the other side, doesn't matter. If you get to the other side first, you win. So each of them come up with a different strategy. Let's call this one Canoeist A. Canoeist A decides to paddle upstream. Canoeist B says he's going to go straight across. And Canoeist C says he's going to go downstream. B, C. My question is, who wins? Or is it another 3-way tie? Or 2-way tie? Who knows? Who wins? So pause the video here. Take a few minutes to think of it. And also make sure when you decide who wins, give a reason, right? Explain why you think that. Okay, so I'm assuming you've unpaused the video now. Now I love doing this question in class because most of the time I get a nice 3-way split. Right? If there's 30 people in the class, around 10 will vote for A and 10 for B and 10 for C. And it's like that because I can explain to you why each would win, but only one of them's right. And so let me tell you the reasons why people go with each one. A lot of people will say A. Why will people say A? Well, they'll say A because if they're heading upstream, they will be able to cancel out, if they head upstream at the right angle, they'll be able to cancel out the current going downstream, and therefore they will paddle straight across and have to travel the least distance to get across the river and will therefore win. Okay, what about B? People will say B says, well, if we paddle straight downstream, we'll be able to head to the other side of the river faster than anybody else, even though we're going to end up somewhere downstream. We'll get to the other side first. Okay, that's a good reason as well. What about C? And people with C says, well, if I head with the current, it's going to speed me up, and therefore I will be moving faster than any of the other canoeists, and we'll get to the other side of the river first. So these are all great strategies, but only one of them can win. I'll give you a hint, it's not a 2 or 3-way tie. Only one wins. So take another minute now that I've given you those ideas. If you want to change your answer, change it. If you don't, okay. Pause the video and think about it. Okay, so we're back. I'm assuming you've unpaused the video. And if you said B, you're right. B is going to be the one who wins. Why? Let's think of this in terms of components. Okay? So it is true, if we look at the components for A, nothing I said in my previous statements were false. So it's possible this component, if you go at the right angle, theta, this component will cancel out this one. And you will head straight across the river with this velocity. And so you will have to travel the least amount of distance, but you still have to travel the same amount of vertical distance across the river as anybody else. Okay? And you're going to be moving with that speed. Now, B is going to be pushed this way. And therefore, the B's velocity is going to be slightly downstream. He'll end up somewhere over there. But if we just look at components, this is the component, and he's paddling across the river. And the distance across the river is the same for everybody. So if we just look at this vertical component, B's vertical component is greater than A's, and it's greater than C's as well. C will be, let me actually add the velocities here. C will be pushed in this direction and will be heading faster than anyone else. C's hypotenuse is greater than anybody's. In this case, it's not the hypotenuse, but C's velocity, what we say is relative to the ground from an observer standing over here, would be greater than anyone else's. However, its x component of that velocity, vertical y component of that velocity, is, if it's at the same angle as A, the same as A. So if A and C are at the same angle, they'll get to the other side at the same time. C will have traveled a much further distance. He'll be way downstream, but he'll reach the other side at the same time as A, if the angles are the same. Okay. E, however, will make it to the other side first. Okay, so that's the answer to that question. But now let's talk about adding velocities, because it's important, especially for if you're traveling in a fluid like a boat on water or a plane in the air, right? If you're moving in one direction, let's say this direction, that's where you've pointed your plane, that's where you're aiming, but there's a wind pushing you, right? Like this. Right? It's going to push you like this, and therefore you're going to actually travel, according to an observer on the ground, in this direction. What I'll do is I'll post a video, so you can look them up yourself on YouTube, just an airplane landing in heavy winds. And it looks pretty scary, but it's also quite interesting, because if you have the runway like this, your plane does not come in perfectly aligned with the runway. If there's a wind pushing it, the plane will be pointed in this direction, but yet it moves perfectly straight down the runway. Why? It's heading in this direction, but the wind is pushing it like this, so it's doing this. Right? And that's very difficult to land, because once all your wheels hit the ground, suddenly your plane wants to move this way. All the forces are telling it on the wheels with the ground, those frictional forces telling it to move this way, but we're moving that way, and so the plane can start tipping, and if it's doing too much, its wings can hit the ground and cause a very bad accident. So a lot of the times planes will not land in heavy winds. So if you're on a plane and you're almost at your destination, but they say they're either going to circle the area or they're going somewhere else to land, it's probably because it's heavy winds and it's too dangerous to land there. So don't be frustrated, because it's better to arrive safe. So let's go over some terms. So these terms are on your sheet. We have airspeed, wind speed, ground speed, and heading. Airspeed is the speed of a plane relative to air. So we usually write it like this: the speed of the plane relative to the air. And of course that's a vector. So that would be airspeed. Okay. So what does airspeed mean relative to the air? Well, this is probably the hardest one to visualize. So let's come back to it. Let's go to wind and ground speed. Wind and ground speed are actually quite easy to visualize. Wind speed is the speed of the wind, but since I'm using A, I'm going to write speed of the air relative to ground. I mean, this you'll hear all the time on the weather reports, right? The wind's traveling at 15 kilometers per hour today. Well, that's relative to people on the ground. That's what you would feel the wind push against you, the leaves, the trees, everything. Okay, and then of course you have ground speed. That's the velocity of, in this case we're talking about a plane, so velocity of the plane relative to the ground. So again, that would be the same as if you are standing on the ground and you look up and see a plane, the direction and speed you see, or if you could measure, that plane moving would be this velocity. So now let's come back and say, well, what's that velocity? Let's go back to our plane trying to land here. Now, plane relative to the ground is obviously straight down the runway, because that's what we observe standing on the ground, and this is the ground. Air relative to the ground, if we're going like this, the air is pushing in this direction in our example. And so if you have like wind towers or something that are blowing, they'll be blowing in that direction. Okay, so what is plane relative to the air? Well, that's actually this direction. It sounds weird because like, wait, we don't see the plane doing that. Well, no, of course not, because we see this, right? And we see this. If we're standing on the ground, we see the velocities relative. This one's dead. We see the velocities relative to the ground. We don't see the velocity relative to air. So try to imagine it like this. Let's say we put a balloon. Okay, a balloon's filled with helium and it's being pushed with the air. So it's moving with the air. Okay, so it has the point of view of the air. And so whatever that balloon sees, that's going to be the velocity of the plane relative to the air. So let's, let me just get rid of all these. Let's start the balloon off over here. And we're going to start our plane. Here's my plane. It's a square. Don't jump. Here's my plane. Now, from our point of view, the balloon's moving with the air. So the balloon is moving in this direction. Okay, that's our wind speed. And our plane is moving in this direction. That's our ground speed. But what does this see? Now, from the balloon's point of view, it's not moving at all. So we're not just going to ignore that. But as time moves on, the balloon does get closer and closer, right? And closer. But if the balloon feels it's not the one moving, what the balloon sees, or what the air sees, is all of this, the ground and the plane, moving closer and closer and closer to it. And so it feels like the velocity of this plane is actually in that direction. It's still moving down in one component and across in the other component from the air or from that balloon's point of view. Okay, if you need to take a minute and just watch that explanation again, or think about it, or maybe skip ahead to that video of the plane trying to land on a runway, go ahead, pause the video, and we'll continue with our second example when you're done. All right, so we're back, and before we go on to the second example, we have one more term I wanted to go over, and that's heading. Heading is the direction in which the plane is aimed. So if we went back to our, just erase this, but if we went back to that one, we went back to our runway example. Okay, the plane is heading in this direction, even though from our point of view it's moving in this direction. So that's what heading means. So knowing all of this, let's try an example. Doing example number 2 on the back. So we have a helicopter travels with an airspeed of 55 meters per second. So remember, airspeed is the velocity, in this case, of the helicopter relative to the air, and that's 55 meters per second. And this is the helicopter heads in the direction of 35 degrees north of west. So the heading is actually the direction for our airspeed. So we can write the direction as, what was it? West 35 degrees north. All right, then it says the helicopter, what is the velocity relative to the ground if the wind velocity, so our wind speed, that's the velocity of the air relative to the ground, is 21 meters per second east. And it wants to know the ground speed. Now to figure this out, we use something called the chain rule, where we sort of add the vectors in a chain. So you can see right here, we have two letters that are the same. And those similar letters we're going to connect in a way, in like a chain. So we're going to have the velocity of the helicopter relative to the air, plus the velocity of the air relative to the ground. And so we're essentially creating this chain. And what it equals, it will equal the letters on the outside. So it equals the velocity of the helicopter relative to the ground, which is what we're looking for. So all we need to do is add those two vectors, which we've done before. This is 2 dimensions. We've added vectors, we've added displacement vectors, velocity vectors, we've subtracted vectors. Right? We're getting pretty good at adding vectors in 2 dimensions at this point. So that's what we're going to do. We're going to add these 2 vectors. And again, you could make it a triangle and use sine and cosine law. But what I'm going to do is use components. And it's actually quite easy with components because this vector is technically already broken up into components. It's east. So we're just going to split this one up into components. I'll choose a coordinate system. I'll make east our positive x and north our positive y. All right, and then let's draw this one and split it up into x and y. So this one's west 35 degrees north, like this. It's 55. Here's our components. And so we can write its x component, 55, cos 35, and its y component, 55, sine 35. There, all done. Now, we can add them to figure out our x and y components of our ground speed for the helicopter. So, let's start with x. So we can figure out the velocity of the helicopter with respect to ground in our x component is just going to be the sum of our x components of both of these. So first we have this. Now this is actually negative because it's west. So it means it's negative east. And since we're writing everything in terms of east due to our choice for our coordinate system, we're going to have this minus that. So we have 21 minus 55 cos 35. Plug that into our calculator, we get 24.1 minus 24.1 meters per second east, which is the same as positive 24.1 meters per second west. All right, so there's our x component for ground speed. Now the y component for ground speed is simply this component here. There is no y component for this one because it's perfectly east. So our y component is simply this. And it's north, so it's already in our positive direction. So we have 55 times the sine of 35. And we get 31.5 north. All right, so now that we have our x and y components, we can make our triangle. So we have our x component, which is west at 24.1, and our y component, which is north at 31.5. And so this is the velocity of the helicopter relative to ground. So we need to find its magnitude and its direction. And that's just a nice right angle triangle. So it's magnitude of our velocity of the helicopter with respect to ground. You can just use Pythagorean theorem, which is 24.1 squared plus 31.5 squared. And that's going to equal, I think it's 39.6. But since we need to have our answer in 2 significant digits, I'm going to write 40. I should write 4.0 times 10 to the 1, but I'm being lazy. Then we need to find the angle. So the tan of theta is opposite over adjacent, so 31.5 over 24.1, and you'll get theta to be 53 degrees. Okay, then you're done. Then you just need to state the velocity of the helicopter relative to the ground is 40 meters per second at west 53 degrees north. And that's it. And that's actually it for chapter 1. Now usually in class what I like to do is have a quiz for chapter 1, simply because the first unit is actually chapters 1, 2, and 3. Chapter 2, we're going to be starting forces. And actually in grade 11, they split those units, right? You do one on motion, one on forces. In grade 12, it's all one unit. So I'm still going to split it because it's pretty big. But we'll start chapter 2 in our next lesson.